could do this much. Although Thurston had started it, but he was just using C++. But yeah, I think this has been a remarkable success story. And we in India should pick this up as soon as possible. I should also thank Manoj, Professor Manoj Yadav. Yeah, he comes from a group which was developed by Professor Pasi very patiently over the years. And perhaps that was the only group that was working on group theory, mainly, except for some people outside his close contact. And he has arranged these wonderful conferences. So far as I know, this is the second conference. And he has been generous, although I am a geometry topologist. He has invited me, you can see that. He also invited Govindarajan, who is a kind of physicist. So I think this has been a healthy tradition in mathematics. Yeah, before beginning my lecture, I should like to refer to my two papers, the symmetries of surfaces, and this second paper on this algorithmic geometric method in the subgroups of the modular group. This first paper deals with the finite group actions on surfaces. Yeah, you know, you see representations on points. These are the permutation representations. Then you can think of automorphisms of graphs, and then the automorphisms of surfaces. Now, yeah, this subject has deep connections with complex analysis of one variable, and namely the Teichmüller theory. And the study of finite groups on surfaces on a given genus, it amounts to a significant, really the whole information about the singular locus of the corresponding Teichmüller space. But the viewpoint of actually studying the finite group actions for a long time was you take a surface of a given genus and then you study what groups can act and so on and so forth. You can write down some algebraic equations and perhaps you can detect some symmetries and so on. In this paper, we reverse that point of view. There is no good pattern if you know groups acting on genus 3 surface. There is nothing inductive pattern that you can detect the groups acting on genus 4 surfaces. But now if you start from the opposite point of view, you start with a finite group, and then you start asking on which genera it acts. Then there is some uniformity. And so that was discussed in that first paper, and it has been developed in many other papers. I just refer to this paper by Weaver and McLachlan, Talu. Yes. The topic is really not only classifying the groups which act on the surface, but classifying the actions. And I think it is widely open, and I think these computational techniques possibly could help in that. And what Professor Dietrich was talking about, this class graph, co-class graph, is some similar patterns also develop according to in this theory. I'm just telling you, I'm just seeing these pictures, and these pictures seem to match. Secondly, this other paper that was actually constructing fundamental domains for subgroups of the modular group, starting with the modular tessellation, which was referred to in Professor Govindrajan's lectures and some other lectures also. And it was some arithmetic method in terms of fairy fractions. And I think, again, there is probably a lot of scope for more computer work in this area. Not only in this area, but this could possibly generalize to Bianchi groups and other things. So, yeah, I think you can. Yeah, this third paper that gives a short exposition by someone who has done more computations by Kurth and Long. And Sertan, he has developed it further. Yeah. So these are some references. If you see the sorry. Which one? This archive paper, I think it's 2007. Yeah, before coming here, I did not know what the other people were going to speak. So I gave this topic, and I should restrict to my topic. And I'm not really a finite group theorist per se, but I loved finite groups. Fortunately, I was a teaching assistant to an algebra course taught by Brouwer. And he was a very kind man. And I took from him his notes on representations of finite groups. I borrowed it for a month and gave him back. And I learned my subject on representations of finite groups from his notes. Somehow, I might have worked with him, but then I once asked him, teach me some Lie groups. But then he was very kind man. He said, I'm not an expert in this field, and something like that. And so it was just my beginning of mathematical career. I studied more differential geometry later on and so on. But I always loved finite groups, although I do not have much expertise in them. So here I would like to talk with these algorithms for constructions of representations of finite groups or arbitrary fields. So if you see the texts, usual texts, they usually do it over complex numbers or algebraically closed fields. Now if you want to generalize that to arbitrary fields, there is the arithmetic of the field that comes into the picture, and I shall illustrate that in my lecture. I think in a way, where Professor Hiss left his talk, I think this talk can begin. So let me start with the basic setup. Now you can take this off. So let G be a finite group. I don't write everything. And F is a field, and I consider the semi-simple case. So the characteristic of F does not divide the order of G. Then one main object is the group algebra. And this condition implies that it is semi-simple. And for any semi-simple algebra, there is a Berman decomposition. So this is some direct sum of matrix rings as an algebra. And if it is coming from the group, then this K, and if F is algebraically closed, K is the number of irreducible F representations. So representations over the vector spaces over F. And these DIs are some division rings. Yeah. Now but this is abstractly isomorphic too. Now try to construct all these objects in FG itself. That was my interest. So in particular, the identities here, so they correspond to some element here. So let me call that EI. And so EI, these are the principal central idempotents. So I think these words are already known by now, so let me not define them. No, I think this is not principal, this is primitive. So you cannot express them as a sum of two similar central non-trivial idempotents. Yeah. And so one thing is to give the expressions for these all over general fields. These things are known when F is algebraically closed. So in that case, K is the same as number of conjugacy classes. If F is algebraically closed. Now, for studying the representation, as is observed many times in lectures here before, that you don't need to know the images of all the elements. You take the system of generators. So a convenient system of generators with some relations, and all you need to know is rho xi. So this is as an operator, and if you like matrices, then you would also like to get some basis for the vector space. And those bases for V, basis of V, that is related to not necessarily central idempotents. So and correspondingly, if you consider that as a matrix algebra, there is a diagonal algebra. So the idea is to construct all these objects in the group ring using a suitable system of generators and so on. And I think this will appear in a thesis by Soham Pradhan. And I think we have been fairly able to do it for solvable groups. And using the PC generators there for the solvable groups. Now, if F is not algebraically closed, then one can define it, there is a notion of F-conjugacy class. So this is a certain union of conjugacy classes. The usual conjugacy classes. And I can describe some structure for that. If X is in G and order of X is N, then you take the nth cyclotomic polynomial. And you decompose this cyclotomic polynomial over F. Then all the degrees are same. Degree F1x, degree F2x, etc. And so in general, this degree will divide the degree of the cyclotomic polynomial. And moreover, the roots of these, so let zeta be one root. Of F1x in the algebraic closure. Then the other roots are, this is after all a primitive nth root here. And so the other roots of this F1x are also some powers of these. And so let zeta to the R2, zeta to the R3, zeta to the say RD. Let this be the let this be the powers, and here so this R1 is equal to 1, and this sequence does not depend on the index. So this sequence remains the same for F2x, F3x, Fkx, and then the F conjugacy class of X is the conjugacy class of X union conjugacy class of R2 union conjugacy class of XRD. So example, if you take field is R, then CRX is equal to CX union CX inverse. Now the F characters are the usual thing. You take the representation with values in F and you take the traces. And then it is the, it's the Berman witt theorem. Which generalizes the usual Frobenius theorem that the number of F conjugacy classes is the same as number of irreducible, number of F irreducible representations. Now the primitive central idempotence. Corresponding to an irreducible representation. And with character chi. So when F is algebraically closed, let me denote this PCI by E rho. So the standard formula you can find in most textbooks is this, they write this chi1 divided by the order G, chi G inverse G. Now, since the characters are the same, on the conjugacy class, you can also write this. This chi1 is nothing but this, if these are n by n matrices, then this is the degree of rho, and so this is, so this is see a conjugacy class, and let me write C bar for just the sum of the elements in the conjugacy class in the group ring. So this is the usual formula when F is algebraically closed. If F is not algebraically closed, then you take C to be the F conjugacy classes, then that is an almost, this sum gives you an almost idempotent. And instead of this degree rho, it's not the degree of the F representation, but this degree is this Ni. If it is an Ni by Ni matrices over that division ring, that Ni is the is this. So you may call it the reduced degree. So general F then E rho is reduced degree C is the F conjugacy class. Now, why the case, the solvable case works easily because of this index P theorem. So let H be a normal subgroup of G of index P. I do not assume G to be solvable, but just in this setup. And let me tell you, when F algebraically closed, and let me just say omega H irreducible H representations, and similarly omega G irreducible G representations. Then there are these usual maps, omega G to omega H, the restriction map. This is not a map, it's a correspondence. You just restrict a representation and just write down the, without multiplicity, you write down these irreducible components there. And similarly, this induction, the standard induction, then in this case, I think in terms of pictures, so let omega H be this, and omega G be this. So either a representation here splits into P representations. And the representation actually extends. You don't have to extend a vector space. So, yeah, I'm telling you the algebraically closed case. Yeah. So let me say eta in omega h. So either eta extends. So on the same vector space on which H was acting, G also acts. And in that case, extend, but then there are P extensions of this. Or the induced representation is irreducible. So, yeah, this is the first case when it extends, or otherwise, P distinct representations here will induce the same one. And this P is just the conjugates of eta. Yeah, so there is some numerology about this. I will not go into this. But yeah, because of this theorem, then you have to translate that in terms of generators of groups and writing down idempotents, etc., etc. But this is the this is the theorem for the algebraically closed case. If F is not algebraically closed, either it will be the induced representation is irreducible, or it extends, or there is a third category, generalized extension. When F general, you get the third category, generalized extension. I do not have time here, so I will not go into this. But let me just take the first basic case, finite abelian groups. So for the rest of my talk, G will be finite abelian group. So let me just recall, if F algebraically closed, we know that the representations are of degree 1, if and only if. So if the abelian groups are the only groups of degree 1. So this is rho irreducible, degree rho is 1. And actually, we do not need Frobenius theory for this. It is just elementary Jordan canonical form. That itself will tell you this. And if you want to write down the matrices, they are just one by one matrices of G is a finite abelian group is a product of cyclic groups. So you may take a minimal such representation, say Cn1, Cn2, Cnk. minimal such representations. You may take the generators here, y1, y2, yk, and then yi goes to the zeta I, which is nth root of unity. So if you just want matrices, these are one by one matrices, the problem is finished. But it does not answer the finer questions of what are the corresponding principal idempotents, and etc. Now, when f is general, then even this degree is not one. Yeah. Degree rho is not necessarily one. And so the things get more interesting. And there are three organizing principles here. And you can see how some number theory, algebra, everything really comes up in this special case. So the first principle is you first note that now if G is finite abelian, then the map factors through the G endomorphisms here. If G is abelian, and this is irreducible. In this case, this is a division ring. And so the image of rho will be a finite abelian subgroup of a division ring. And what do you know about such finite abelian groups? They are cyclic. So this implies im rho is cyclic. So an arbitrary abelian group, if its irreducible representation will always factor through some cyclic quotient. And if that is the case, then we can actually say what the structure is. Let me just call it a theorem. G a finite abelian group exponent m then for all d dividing m, let HD be the subgroups. These are going to be the kernels of the representation. So where G mod H is a cyclic group of order D. And let me denote by omega 0D the faithful irreducible representations of CD. And so by this above argument, it already says that all the irreducible representations of G are in one-to-one correspondence with uh, with these pairs now, this this is a nice description here. You see, this is an absolute invariant. It does not depend on F. It just depends on G. And the F comes in here. This is an absolute invariant. And this depends on F. This description itself is not sufficient to produce principals, central idempotents, and so on. But you know what exactly what you're talking about. The second organizing principle is a direct product of its p-zero subgroups. Now, if say rho p is an irreducible representation of Gp, and rho q irreducible representation of Gq, where p is not equal to q. In that case, rho p tensor rho q is an irreducible representation of Gp cross Gq. When p is equal to q, this is not true, and that is that is the complication in this story. And this corresponding PCI is just you just multiply those two elements in the group algebra. So in this way, in some sense, you reduce to the case when G is a abelian P group. So you, considering the first observation, I think the important special case G is Cp to the n, cyclic group of order P to the n. So in this case, the group algebra is clearly this polynomial ring in one variable divided by the ideal generated by x to the Pn minus 1. And now the field will come into the picture, how this x to the p to the n minus 1 factors in F. So the problem is reduced to the factorization of polynomials. So if Ix irreducible over F. And then by the Chinese remainder theorem, this algebra is isomorphic to F. First the copy of F, and then I think we are really going to the beginning of the representation theory. Now this is irreducible, therefore this is a field. And now G will act on this. So here G is the generated by X. And X just acts on this by multiplication by this class of X. This is not a say. This is an indeterminate. So this is the class of indeterminate in this. And so that's a field. So you consider this as a semisimple algebra. And this is actually the Berman decomposition of the group algebra. So, and so this representation on this part, the representation is irreducible because this polynomial is irreducible. We are using the word irreducible in two different senses. But that is where the terminology for the group representation probably came in. And if you want a matrix, then this is the companion matrix for Fix. And you take the generators 1, x square, x to the d minus 1, where d is the degree of Fix, and you write down the companion matrix. This is your irreducible representation. But still the question is to write down the corresponding principal central idempotents. This is just the abstract Berman decomposition. We have to make it concrete. Now the computation of E row. And here the story starts. So, you first take F algebraically closed. And now your G is Cp to the n, but now you just don't take the minimal generator here, but just take this long generators, x1, x2, xn, where x1 to the p is identity. X2 to the p is x1 x3 to the p is x2, and so on. And let me denote it by this x is an indeterminate, 1 over p, 1 plus x squared up to x to the p minus 1. And now the theorem, the principal central idempotents are, I just write down e to the zeta 1 x1, e to the zeta 2 x2. These are all elements in the group algebra, and I'm multiplying them. E to the zeta n xn, where zeta n, let me introduce a notation here. The nth roots of unity. See, this is an interesting expression because our usual, the standard formula for writing down the idempotents, which works for general groups, in this case, all the representations are one-dimensional. So there are p to the n terms. Whereas here, each term contains only p terms. And so there are only pn terms. So I think this is a computational advantage, even in the algebraically closed case. And now, of course, the number of irreducible representations is p to the n. Now, let me take an extreme case where f such that all cyclotomic polynomials are irreducible. For instance, the rationals. Now, let's take G0 contained in G1, which is generated by in these long generators X1, contained in G2, long generators X1, X2, and so on. And you can, if you want, you can use that index p-theorem if you like. So you start building up this kind of Bratelli diagram. Suppose the group was just G1. So here is the trivial representation for which the idempotent is EX1. Now, I don't know the but in this case, there is only one irreducible representation. One non-trivial irreducible representation. So without doing any calculation, I know that sum of these has to be 1. So I'm denoting this by EX1 prime, which is 1 minus EX1. So this is the complete story. Oh. I think let me just at least finish this. Then EX1, EX2. This will, this is on the G2 level. then ex1, ex2 prime. And here it is the same e prime x1. But this is the representation of G2, and the degrees are different. Yeah, and so on. So here the first will split into two, and then it will continue. So, the number of irreducible representations is just n plus 1, independent of the prime. Now the real fun starts when this condition is not satisfied. Then you have to worry about, I think this is already some interesting. The general case, then F, so then there is an invariant. This is the max K such that all the kth root of unity lie in F, if it is finite, if it exists. And otherwise, infinity, otherwise. Now you have to deal with the cases. This group is Cp to the n. So if n is less than L, so it is like the algebraically closed case at this level. And you get the usual story. N is less than or equal to L. But n is greater than L. Then you have to worry about how that thing factors. And you suppose, yes, there is again subcases here. So here how the number theory comes in. Suppose L is greater than 0. So there are at least p roots of unity, but not p to the L plus 1 root of unity. Then how will this factor? So let me just denote by mu I0. Zeta is a primitive root of unity. Primitive p to the I root of 1. And without that 0, I denote everything. So, so this is, I could as well write x minus zeta in mu L. But now, this is at least some decomposition, x to the p minus zeta in mu L sub 0. Then x to the p square minus zeta, where zeta is again mu L. Now, question is, are these irreducible? Now, if p is greater than or equal to 3, again number theory comes in, then all these are irreducible. Because the zeta raised to 1 over p does not belong to the field by definition when zeta is in mu L 0. And then it's the Kummer's theory that will tell you that all these are irreducible. And then correspondingly, you also get this PCI diagram and so on. So the case P equals 2, this is actually false. But then the case is more and more complicated. But I think it can be handled, I think. Yeah, that's it. Thank you. So this was probably understandable to everybody.